Okay, everybody. So what we're going to be looking at today is kind of the parts of section 6.2 that we didn't cover in the original lecture. So basically, I stopped before we covered Flux or did any of the applications problems. So what we're going to do now is just go over that briefly, and hopefully this won't be too long of a video. So let's just recall where we were. So uh, in part one, I'll say, of the 6.2 lecture, we covered, what did we cover? Um, line integrals. But we covered line integrals, two types, right? We had, first case, we were covering line integral of a scalar function, which, if you remember, looked like this. So they would ask you to come up with the integral over a curve of just f of xy or f of xy ds. And when you unpack that into how you were actually going to solve it, you were going to make an integral from a to b of f of, you plug in r, which is your parameterization of curve, r of t, and then your ds was the magnitude of that r prime dt, right? This is where c is given by r of t, or t between some a and some b, right? So we did line integrals of scalar functions, and also we did line integrals of vector fields, line integral of a vector field. Okay, so where I want to start with that is just by the notation here. Hold on a second. Yeah. So if you remember, they were given this way to start with, integral over c, and they wrote f dot t ds, like that. And then that turned out to not be how you actually did them, because what you ended up doing was you had an integral from a to b. Your f, you were going to plug in the parameterization for the curve again. The t, this was the unit, not unit, unit tangent. And the unit tangent was r prime of t over the magnitude of r prime of t to make it a unit vector. And then the ds was the magnitude of r prime again, dt, right? ds here is the same as ds up here, which was that. And then, of course, what happened was that the r primes canceled, and what you ended up using was this form of it, right? A to b, capital F of r of t. Then you just had, I lost a dot product here. That should have been a dot. Dot product with r prime of t, and then dt. And it turned out that you didn't need the magnitude of r prime at all, because it just canceled each other out. Okay, and what I did want to bring your attention to was where it says unit tangent. That's what t was, even though we didn't, you didn't think about that very hard while you were solving problems. Okay, and that's how you arrived at this equation, which is the one that you actually used. So you ended up using this one when you were doing a line integral of a scalar function, and you ended up using this formula when you were doing a line integral of a vector field. Okay, and that's where we were. Now, the idea of flux is a little bit different. So here's the idea of flux. So the flux through a curve, C, let me see how they word this. Like, what words did they use? Give me 1 second here. Okay, So the flux through a curve C, where a um, fluid has velocity field F. So what's that mean? What that means is that uh, at every point, x, y or x, y, z, the fluid at that point at x, y, z has velocity capital F of x, y, z, right? So the vector field are like the flow lines of the fluid. Okay, so what does that mean? So the flux through a curve C where fluid has velocity field F represents, or is, I should say, is the quantity of fluid that's flowing through that. So let me see how they again say that. Yeah. So is the rate at which the fluid is flowing through the curve C. So let me just draw a little picture for you here, right? So if you put like a curve C like this, right? And I'll even do that. Put an arrow on it. Let's say we have a velocity field like this. It doesn't have to be like at right angles or anything. It's just kind of drawing one that's kind of flowing through that curve, right? So if that's F, right, if that's the velocity of the fluid at every point, right, you can see that some of the fluid is going right across this curve. And well, how much of the fluid is going through that curve? That's what flux is. So some fluid is flowing straight through, is I'll say crossing the curve C. Uh, what's the rate that it's doing that? What is the rate at which the fluid is moving through C? Answer, the flux of F through C. So does that make sense? So you're calculating the amount of fluid that's flowing through a little piece of, well, this curve right here. Um, and we're going to add that up, and that's what flux is. Okay. Now, in order to do that, though, it's we're going to need to figure out like how to define that. And I don't really want to do too much deriving that. We can spend some time, but I don't really want to. So the punchline is going to be this. So you can see the book for details, but the idea is that instead of this integral over C of f dot t ds, you will have the integral of C of f dot in ds. So the difference is that t is the unit tangent vector, which is r prime over the magnitude of r prime, and in is the unit normal vector to the curve. which is what? Well, we're gonna talk about that. But first of all, why is that what it is? Well, if you kind of think about my drawing that I did and it's already gone, why do we use the normal vector? Let me draw the picture and we will see. Okay, so let's say this is C with parameterization. My neighbors are screaming again. Just one of them, I guess. This guy just always yells all day. All right, so let's say you have the C like that, and then you've got this. Let's say that our F could look any way, but let's say it's just kind of going straight up for sake of argument here. Right? So how much actually ends up going through that curve is actually related to the normal to the curve, right? If I draw this normal here like this, so I don't know why I drew that crooked. Should just draw it straight, easier to read. Right. So if that red is the unit normal here, right, pointing straight out from that curve, the idea is when the fluid and the normal are in the same direction, then more of the fluid is going to be crossing this curve, right? If I drew my field lines, instead of the field lines that I drew, if I drew my field lines like this, for example, what if my field lines were like this? How much fluid would be flowing through the curve C? None, right? Like if the fluid is basically flowing along the curve, none of it's really crossing through, right? In order to cross through, it needs to be going in the same direction as the normal. And that's why you're doing a line integral to calculate how much is going through here, but you need to know the normal vector instead of the tangent vector. Because when the fluid lines and the normal lines are pointing in the same direction, that's when fluid is crossing through C. Okay, so that's why it is the way it is. The actual derivation you can see the book for. Um, so idea, when the normal vector and F are pointing in the same direction, that's when you have a lot of flow across C. Fluid is crossing through C. Okay, so that's why we're going to do that dot product. So basically, if the dot product between these is 0, then that would mean that the fluid is actually 90 degrees away from the curve. And if the fluid was flowing along the direction of the curve, that would mean it's not going through the curve. So, yeah, so that's it. So that's why we see the normal vector in the definition. Okay, I'm not going to justify that anymore. And you know that the dot product between these two vectors is related to the angle between them. So the closer these are to pointing in the same direction, the more fluid is flowing through C. Okay, so that's enough. Now, of course, we don't use that definition, just like we don't use the original one for we don't use the version with the tangent vector. Like we don't use this to calculate integrals, right? Well, we're not going to use this to calculate integrals either. Um, so our definition says this says the flux of F across C is the line integral over C of f dot unit normal ds. Okay, where n over magnitude n is the unit normal vector to C. Okay, we don't use that definition though. For computation. Instead, we do this. Okay, so just like before, you have the integral over C of f dot n over magnitude n ds, but we're going to have a parameterization. C is given by r of t, where t is in between a and b. Then you're going to integrate from a and b. You're going to have to plug in your parameterization in for r. You've got your normal vector, which is n over magnitude n, but then your ds is still the same ds as before. Now, here's the thing though. We haven't talked about calculating normal vectors, but the normal vector and r prime are going to have the same magnitude. But magnitude n equals magnitude r prime. And I'll put like an asterisk there because we'll justify that. So we get integral over C of f dot n over n ds is equal to, and this is the one that we're actually going to use, it's going to be the integral from a to b. It's going to be f, you're going to plug in the r, and then it's simply going to be dot n, which I guess is a function of t, and then dt. And the reason for that is going to be because these cancel because they're equal. Okay, so if you compare this right here to the definition we had at the beginning, to this one right here, the only difference between this and what we have down at the bottom is that this is r prime and this is n. So that's the only difference, just right here. This is the only difference. And what is that vector? Well, it's either, there's two possibilities. Either the n vector is going to be y prime here, x prime here, and then a negative right here, or negative y prime here, x prime here. So they're the same. It's just one has a negative on the second term and the other one has a negative on the first term. And then just so we're aware, asterisk, the asterisk is why are these equal? The reason these are equal is because, recall r prime is just, you take the derivative of x and you take the derivative of y. So what's happening here is r prime is x prime y prime, and the normal vector, we're just switching them and then making one of them negative. So to get n, you find r prime, switch the components, the x and y components, and make one of them negative. Not make one negative, but add a minus sign to one of them. Okay. And that's also the reason I said that that's the asterisk is because if you look at these two things, r prime and n, of course they're going to have the same magnitude because when you do the magnitude, you're going to square this and add them up. And that's going to be the same as if you square this and add them up. So that's what's going on here. That's why I can say that these two things have the same magnitude because literally they have the same x and y components. They're just swapped and one's made negative. Okay. And the reason that's all you do is because recall that on this graph, this is the direction that r prime is. So r prime is parallel to the curve and the normal vector is 90 degrees away. And the easiest way to find a vector 90 degrees away from another vector is to switch the components and make one of them negative. So that's that. Now, which one do you switch? Which one do you switch the sign on? Whichever. You do the one that, like, sometimes they tell you that the normal is supposed to point in a particular direction, and then you have to figure it out. Well, sometimes they say. And the way they would tell you is like this, for example. So, like, let's say you have a curve like this. They could say, like, that's C, and then they could say, normal should point up, or something similar. And then you would know, like, oh, well, if this is my curve and the normal needs to point up, then, you know, this would be wrong, right? So that's the difference between these two things is they point in opposite directions. So, right, one of these is the one that they want you to use and the other one isn't. Now, what's the difference between them? Well, you're going to be finding how much fluid is going in the direction of the normal. So if your normal points in the opposite direction, you know, you might calculate, well, you will calculate the negative of the number that you intend to calculate. Okay. So, yeah. So the flux integral will compute the rate of the fluid in the direction of the normal. So if you get it backwards, you just get the negative of of the answer you want. Okay. So enough said about that. Let's we can do a problem. Let's do a problem. Um, okay. So let's try one. Okay. So let's say I say calculate the flux um, of F equals 2x comma 2y across, I'll say the top of a circle oriented counterclockwise. The normal should point up. And what that means is the y component should be positive. Not that it has to be straight up. Okay, so here's a problem. So if we look at the picture for this, then the f just points out, just straight out from 0, 0. Okay, so that's what f does. And then, of course, the unit circle is the unit circle. Can we draw a circle, please? No, we cannot. Okay. I'll just draw it. Okay, so this is your C. Okay, and I drew arrow to indicate that it's going in counterclockwise direction. Okay, so with that said, we should just be able to set this up now, honestly. It shouldn't be that hard. So the only difference is that we're going to need the normal vector instead of r prime. So normally you would parameterize your curve, C. So for a unit circle, we would normally use a parameterization like cosine t, sine t. And if the radius was not 1, you'd put the number out front, right? But our radius is 1, so it's just cosine t, sine t. Now what about t? We need limits of integration for t are going to be, in this case, 0 and pi, right? Because we only want this top half. The next thing you need to do is we're going to need the unit normal, but before we do that, we're going to need the r prime, right? So let's compute r prime. So r prime of t is just going to be the derivative of this one right here. So it's going to be negative sine t, comma, cosine t. All right, then to get the normal vector, which I'll make a separate step here, get in by reversing the components and making one negative. Now, I shouldn't say making one negative, adding a negative sign. All right, so what do we do? So our normal vector, if we just switch the components on r prime, we'll put the cosine first, we'll put the negative sign second, and we need to add a negative to one or the other. So add a minus sign to one of these. Okay, and the one that we should do is actually the second one. Because you can just check that your normal vector is going to point up. If we check it here, hold on. So like, for example, if you check the direction of n at, let's say, t equals pi over 2, you get n of pi over 2, which is cosine pi over 2, comma, sine pi over 2, which is 0, 1. And that's up, right? So if you, this is crooked, but I don't care now. So if you look at your curve, can't draw half a circle. It always wants to turn it into a parabola. Always wants to turn it into a parabola. Please stop. Hey, stop. Just let me draw half a circle. Just let me draw it and let it stay. Okay, did it. So if you check at pi over 2, right? That's pi over 2. N should be pointing up, not down. So if you added the minus to the x component, it would have pointed down. Right? So that's why back here where I say we have to add the minus somewhere, well, if I had added it here, right, then what I would have gotten is negative, negative. And then when you go to plug in pi over 2, this would have been 0 still, but this would have been negative 1, and that would have just pointed straight down. We didn't want it to point straight down. We wanted it to point up. That's why we did what we did. Okay? So yeah, so that's why we did what we did. It's, there's a lot of like text there that didn't need to be there if we're calculating this. So anyway, once we've done that, are we on step 4, I think? We should be able to set up our integral. Because we know we have f is 2x comma 2y. We know we have r is simply cosine t sine t. We also have n, which turns out to also be cosine t sine t, right? That's not usual, right? Usually r and n are different, but that doesn't matter. Just kind of a comment here. It's because when you take the derivative of a cosine, you get a sine, and when you take the derivative of a sine, you get a cosine. And then if you switch the components, then basically we switched them and then switched them, right? Sine went to cosine, which went back to sine, and cosine went to sine, which went back to cosine. So that's why these ended up the same. But that's not a usual situation. Of course, we know the values for t are 0 and pi, right? So that's everything you need to set up your integral now, right? Because the integral for flux is the integral over c of f dot n ds, but for us, that's the integral from a to b. Should I write it again? I will. Dang it. A to b, f, but you plug in your r, then you've got your n, and then you've got your dt, dot n. Okay, so we put everything in here. So now we can go a and b are 0 and pi. F is here, 2x, 2y, but we're plugging in the r. So we get 2 cos t, 2 sine t, that's f of r, dot with n, which is cos t sine t, and then just dt. So once you actually get to the point of setting up the integral, it's just as easy to set up as any other line integral. It's just that this is n instead of r, right? This is n. All right, integrate. So you have 0 to pi. We would have to do this dot product, which is going to be 2 cosine squared t plus 2 sine squared t dt. Oh, well, look at that. That's going to be just the integral of 2 dt. That's weird. Um, but it is what it is. And so when we do that, we are going to get 2t from 0 to pi, and that's going to end up 2 pi. And so that would be the flux. Perfect. All right. So let's see. Let's do one more of these. Calculate. Actually, I'm probably just going to set up the integral. Calculate the flux of f equals x plus y f equals x plus y comma 2y across the line segment zero, 0 to 2, 3, where the curve curve is oriented left to right. All right. So I don't really care what the f looks like, but what I do care about is that we have 0, 0, and then we have, let's say, 2, 1, 2, 3, like this. That's your C. All right. Now they didn't say which way to orient the normal. So we'll just see how it happened. Okay, so calculate the flux across. So what do? Step 1 is going to be parameterize C. So for this one, your x of t and your y of t, we talked about parameterizing line segments. What you can do is simply start out with your first, you have 0, 0, and you have 2, 3. And so you can go like 0, 0, plus, plus, and then you basically calculate a slope here. Like, so for x, it would be 2 minus 0 t, 3 minus 0 t, like that is the general way you do this. So you end up with r of t is going to be simply 2t comma 3t with t going between 0 and 1. So there's my parameterization, right? You plug in a 0, you get 0, 0. You plug in a 1, you're going to get 2, 3. So it does that. So that's parameterizing line segment. The next thing we need is we're going to need r prime. So let us do that. R prime is going to be 2 comma 3. All right, now what's that say about n? So n is either 3, 2 with the negative there, or n is either 3, 2 with the negative there, right? You use whichever one you wanted. So if you wanted it pointing to the right, for example, you would take the second one. Why do we want it pointing right? Nobody said we did, but it could be pointing to the right, right? I mean, we have two choices, right or left. So it could have been one or the other. I'll just take this one. Okay. So then we can set up our integral. So what we want is the integral from a to b, f with r plugged in, dot n dt. So we get the integral from, we're going to go 0 to 1 because that's what we have for r. Then we need to plug 2t, 3t into f, which f is way up here, right? Let's move this down here, right? We have this, and r was, what was it? 2t, 3t? 2t, 3t? Yeah. So when we plug that in, f of r, we're going to get the vector x plus y is 2t plus 3t, comma 2y, which is 2 times 3t. Then dot product with the normal vector, which we're going to use 3, negative 2, because we said, and there you go, right? So that's f of r, that's in, and there you go. So then you would integrate, and I'm not going to because of time, but what you would be integrating would be the dot product of these, right? So you would have to do 2t plus 3t is 5t times 3 plus, then you got 6t times negative 2. Okay, I guess we can just finish it. 0 to 1. So what do we got? We have 15t minus 12t, so that's 3t, right? And then you'd just be integrating this. So you'd go 3t squared over 2 from 0 to 1, and that looks like 3 halves. Um, so there's your flux. All right, so that is how you calculate flux. And then one more application, and then I think that'll be it. This is just going to be kind of more of a note rather than like a real application here. Um, so I'm just going to say mass. Okay. So basically this, if you have a curve C with parameterization, R of t, again, t is going to be between A and B. So there's your C. And then you also have that, like a wire, for example. And with the wire with density at xy given by, let's say, rho of xy, and that would be the units on that would be mass per unit length. Okay. That's along C. Right. So the wire, like the curve is the wire basically, right? That's what we're saying here. Just follows the wire. Or rather, the wire follows the curve is what I should say, but I guess that's technically the same thing. Um, in that case, then your total mass is of the wire is just going to be a line integral. So you're just going to integrate over C of the density function. That's it. And of course, the way you actually calculate that would be it'd be an integral from A to B. You'd have your rho, you plug in your parameterization like we always do, and then your ds is magnitude of r prime, and then dt. So this is just a regular line integral. There's nothing special to it. This is a regular line integral. Nothing crazy happening there. Okay, so let me see if I can find like a simple example here. Okay. Calculate the mass of a spring with a shape given by r of t equals 2, no, t 2 cos t 2 sine t for 0 less than t less than pi over 2 with density rho equals, and I'm not going to write xyz, e to the x plus yz, and that is in kilograms per meter. Okay. And so this is like, you've got an arc there, because this is part of a helix, right? But we've only got part of the helix. Okay. So it's just a curve of wire. And again, this is going to be super straightforward. You need your r, but it was already given for us, so we don't have to do anything. You compute your r prime, which is 1 negative 2 sine t 2 cos t. We set up our integral. We don't need, there's no normal here, right? We only needed the normal for flux. So mass is equal to the integral from a to b. We're going to take rho, we're going to plug in r, and then we're going to multiply by the magnitude of r prime, and then we're going to have dt. So this integral is going to be 0 to pi over 2. Those were the given limits for t. We need to plug the parameterization in for rho. So you have e to the x, but x is t, so that's e to the t, plus yz, which is these two things multiplied, for sine t cos t, times the magnitude of r prime, that's a square root of 1 squared plus 2 sine t squared plus 2 cos t squared, and then a dt on the end. I notice I left off a minus sign, but the minus sign doesn't matter because we're squaring that. So you work this all out. This is actually going to be 4 cosine squared, 4 sine squared. That adds up to 4. 4 plus 1 is 5. So after you do all the work, that's just 5 dt. Okay. So then we can just integrate to finish this up, I guess. We're just about done. So I'll just put the square root 5 on the outside from this. And if we're looking for an antiderivative, the antiderivative of e to the t is simply e to the t. The antiderivative of sine t cosine t, well, that's your u, that's your du, right? I don't really need to write it out. U equals sine t, I just did, cos t dt. And so when you integrate u du, you get u squared over 2. So you end up with 4 times, and then it would be sine squared t over 2. And then that goes from 0 to pi over 2. So, you can work this out. Square root 5, put in pi over 2, you get e to the pi over 2 plus 2 sine pi over 2. The squared is just on the sine squared, minus root 5, and we're putting in the 0, e to the 0 plus 2 sine 0 squared. So we end up with 5 e to the pi over 2 Sine of pi over 2 is going to be 1. So that's going to be 2 there. Minus root 5, 1 plus 0. So overall, what do we get? We end up with root 5, and it looks like we're going to have e to the pi over 2 plus 2 minus 1. So plus 1. And that is your mass of the wire. So we just do the integral is what it comes down to. I guess it would be in kilograms. So we did it. What was the point there? The main point there is just if you're calculating mass, you integrate density, period. Right? We've done that before. We're doing it again. But this time it's density along a curve instead of density in space. All right. So I think that's it for now. I will talk to you guys later. Hopefully this helps with the homework.